Okay, so good morning and welcome to today's lecture. Just to confirm, Professor Chakraborty, you can hear me, right?
Yes, I can hear.
Okay, good. Okay, so we will do a quick recap of what we discussed yesterday. We have been talking about Bitcoin, how the blocks are organized and how the blocks are generated. And we'll also see what these transactions are all about, how the transactions are executed, quote unquote executed, what it means to actually carry out the transactions, how that means that Bitcoin is transferred from one user to another. First of all, we'll focus on the creation of the blocks, especially the block header. And as we said, the block contains a header and the set of transactions. We also talked about the number of transactions. As we have seen, the typical size of the block, let us consider it is 1 MB, and that would contain a number of transactions. And also we have seen that the important part is to generate a block so that its hash, which is there in the block header, satisfies certain properties, which is the number of leading zeros. And this process of generating the block, which boils down to computing the hash with desired properties. Okay, so that is what is called mining. Okay, so that mining means that we want this hash hk to be obtained, which will be hash of hk minus 1, the previous hash, the timestamp, nonce, and something more as we'll discuss today. Okay, and the header contains some more information about the block, and we will also take a look at that. Now, we mentioned that this whole notion of mining a block boils down to finding a nonce that results in the hash with the required properties. And doing that essentially means we have to try out a very large number of such nonce and keep generating the hashes and matching with the desired level of quote unquote difficulty, okay, which is that number of leading zeros. Now, that means that one has to invest a lot of computing power to carry out so many hashes so that one can hit upon the nonce resulting in the appropriate hash. And that means a lot of hardware would be required. It is not something you can do on a regular PC and get so many hashes done. And most of the, as we'll see, that the ASIC hardware, the application specific ICs which are meant for generating such hashes in a very efficient manner, they can generate order of tera hashes a second. So these are pretty powerful hardware. So what we'll do is that we'll see that how this generation is done. Okay, the hash. Of course, as we understand that we'll not be able to generate the hashes with the desired property because it is very computation intensive. And if you remember in one of our earlier classes on crypto primitives, we showed there was one site where we were giving the number of leading zeros maybe 1, and then it could find the nonce, maybe that the value of 11 of the nonce was resulting in maybe say 1 leading zero for a given text of hello world. Okay, but as we gave the number of zeros to be large, maybe we gave maybe some 7 or 8, you saw that the site did not work because it had to carry out too many hashes and it was not responding. So very quickly we'll have that difficulty. Okay, now the block identifier, okay, the hash of the current block header, okay, and the hash that is done is what is called a double SHA-256. So SHA-256 is applied twice. Okay, whatever we get after the first application, that is done, that is one on top of it again SHA-256 is applied. And there are a few other interesting concepts that are there. So I'll cover those points. And of course, it makes so the hashes that are there in the block header. One is the block hash itself. Okay, the Merkle root is also a hash. The previous block hash is used to compute the current block hash, but it is not included in the current block header as was asked in the class yesterday. So it does not add any extra value, and also other than it will take up some space. Now, the component, the 6 components that are used for computing the current hash are these ones: the timestamp when the current block is being generated, the previous block's hash, the Merkle root of the set of transactions in this block, the difficulty bits, okay, nonce, and compute the current hash. Okay. Now, what is the difficulty bits? I will go back to the previous slide after we have seen, okay, how it actually works. So what we'll do is that now I'll show you that how one can check that the hash that is there in the current block is indeed correct or not. Okay, so we are not in a position to generate that hash, but we'll check or verify whether that hash is correct. Okay, so let us go to a site. So if you see this site, okay, so it is having this Bitcoin block hash verification tool. Okay, and you see that I have to give these as inputs. Okay, these 6 values as was mentioned in our slides. These 6 values. Okay, and what we'll do is that we will go to one of the blocks. Okay, so if we go to one of the blocks, say, let me just pick up. So these are, as you see, these are live blocks, and you see that one was generated today at 11:07, the other was 10:48, and so on. So I'm just picking up at random one of them, say 697,634. So you can see this is 697,634, and I picked it up from this btc.com site for a particular reason. Okay, I'll explain why I picked it up. Now what I'll do is that here I'll feed in the data for this block. Okay, so see, the first one is version. So there is this version. So let us pick up this. And what is this version I will discuss. But first I just blindly pick this up. And it also says that I have to give it in hex. So I can give it in hex. So 0x if we write, so it is clear it is in hex. I'll come to previous hash, but Merkle root. So again, you see that the Merkle root is given here. Okay, I just pick it up from here. And remember, I am doing it from btc.com website. And the nonce. This is the nonce that the miner actually came up with. Okay, so that was the holy grail, getting the nonce. But now it is given to us, so I just pick it up. Okay, and I put in here the timestamp. Now, timestamp, this is something you have to keep in mind. You see the timestamp that is displayed here, that is given in the local time. Okay, this is 10:31. Okay, but here we have to give this time in terms of UTC. Okay, so if you hover your, I hover the cursor here, I get this time, and I select this and copy it, and then I paste the time here. Okay, and difficulty in bits. So you see this bits that is given here, I pick it up. Okay, sorry, this one is the bits. Okay, so I pick it up and paste it here. Okay, now the previous hash. Okay, so these are all you see are there in the block header of the current block, which is the 697,634. Okay, up to this, you can see everything I have picked up from here. Now the previous block, I do what I can do is that I can just click on this left arrow, and I can go to 697,633, and its hash is given here. Okay, so I just copy this. Okay, so it is copied. So I paste it here. Okay. So I have got that. Now I go back to my 697,634. Okay, and then I click on calculate block hash. Okay, and then you see I get this as the block hash. Okay, and if you see the block hash here for this current block, it is indeed the same. Okay, so all these zeros 9BC, and also you see zeros 9BC and all. So you see that we have done something interesting, and that is what is all about validating the blocks. Okay, that means that if this person or group who claimed that they have indeed mined this block, And in the process, they could come up with this value of nonce, and this particular uh, um, value of block hash, which satisfies the property. You see, there are a lot of leading zeros, and we'll see that it indeed matches with the requirement. Okay. So how do you know that this is really correct? Whether he's just like that, put certain values here. So we could simply use this technique, okay, where we feed in all the 6 required values, we calculate the block hash, and we get the hash here, which you can easily match with it. Okay. So the point here is that validating the block hash is very, very easy. As you could see, it could do just like that. And out of the components that are there in the block header, this Merkle root, as you can see, and we have discussed. So this is based on the transactions that are there below it. Okay, so this is the content of the transactions in this particular block. And for those transactions, we create the hash and then combine those to create the Merkle tree, and the root of that Merkle tree, that is the Merkle root, that hash is what is there here. Okay. So that means that if we change those ones, as you know, that this will get affected and the same nonce will not work. Okay. So then one will have to again compute the nonce so that we get a hash that satisfies the requirement in terms of the bits. Okay. So that the block hash would be obtained, which will still satisfy those requirements. Okay. And that is going to be very hard, and especially if we have to do it for a large number of blocks. Okay. Now, so that is what I did. Okay. And of these, all the other components are easy to understand. The timestamp, as I said, that we have to pick up the UTC time, previous hash, the Merkle root, the difficulty bits is something I will explain, and nonce and version, as I already mentioned. Now I go back and then pick up the discussion on difficulty we had yesterday, and go into a bit more of details. So this difficulty, that is auto-adjusted, meaning that we would like the average block mining time to be 10 minutes, okay, and with variation in hardware and capability and these the difficulty levels and all, that current difficulty level. So what is done is that the new difficulty level is determined. Okay, and with some time over 2 weeks or so, it takes an average block mining time and determines the difficulty. Now, what is this difficulty all about? Is that when the first block was mined, it had got a difficulty level of this one, which is shown here. Okay, and if you see that it had got these 8 number of leading zeros. Okay, so finding a nonce so that the hash had 8 leading zeros was not that difficult. Okay. And today you see that there are so many number of leading zeros that are here. Okay, so this is for a particular block, may not be the current block. Okay, so now the number of leading zeros that you have to obtain is much more, and hence finding the nonce to satisfy that type of hash, this has become more difficult. Okay, and if people can still have better hardware to reach this quickly within less than 10 minutes, most of the time over a period of 2 weeks, then again maybe the number of zeros will be increased by 1. Okay, and as a result, again people will have to spend more effort. Okay, so that it sticks to that 10-minute time frame. And if it is found that it has become too difficult, then this difficulty also will be reduced. Okay. Now the point is that how we talk about that number of leading zeros and so on here from what is shown here as these bits. Okay. So you see that these bits, it's in hex, it is 170FFAA0. Now how the difficulty level is computed, I will tell you. So let me go to a site, okay, which will tell us how to do this. Okay, so let me go there. Okay. Yeah, so I'll click on this and let me go to this site, which actually explains what that difficulty level is, and it's pretty simple. Okay, so if we consider this particular page here, if you see that this difficulty, okay, let me explain it. So the difficulty is something like this. This in hex, it is, let us assume it is like this, okay? And then we'll pick up for our case, okay? So if it is the hex number is this, now this is, you see that it has got 8 hexadecimal digits, okay? Of which these first 2 they represent index, and the rest 6 they represent what is called the coefficient, okay? So the target is that coefficient multiplied by 2 raised to the power 8 into this index minus 3. So if we substitute these values, okay, so here this coefficient is 29D72D multiplied by 2 raised to the power this 8 into index, which is 17 in hex minus 3. So if we substitute the corresponding decimal values, so we get this value of 4.00 something raised to the power multiplied by 10 raised to the power of 54. Okay. And now if this is converted back to hex, okay, so we get certain number of leading zeros. Okay. So that is how one obtain the required number of zeros that should be there in the hash. So let us try to do something similar for our example also and see what we are getting here. Okay. So let me go back to that block, and let us see what we have is that bits is 0x170FFAA0. So 17, as you can see in hex, it means 23. Okay. And this one, so 0FF AA0. So if I select this, and I'm going to cite that let us convert this hexadecimal to decimal. Okay, so I'm just using that. Okay, I convert and I get a number like this. Okay, so 0FFAA0 that corresponds to this number. Okay, now what we have to do, if we see this particular site, so what I need to do is that 2 raised to the power 8 into 23 minus 3. So in our case also, if we see that in our example, okay, so it is also 117, which is 23. So 23 minus 3 is 20 into 8 is 160. So 2 raised to the power 160. Okay, so 2 raised to the power 160, and then this to be multiplied by what we obtained here, okay, as 1047200. And now if we do this, okay, so let us use maybe a calculator, okay, that we can do 2 raised to the power of 160. Sorry. Okay, is this one, and which we multiply with this number. Okay, so I do a Control C, Control V, and I get something. So I get something which is like 1.53, etc., into 10 raised to the power 54, which is similar to what they had. And now what we do is that we enter this here, okay, and then convert it from decimal to hexadecimal, okay, and we get a number like this, okay, a hex number, okay. I think you are able to follow what I am doing. And then what we'll do is that we'll paste it here, but then it is not in the size that is required for this 256 hexadecimal hash. So what I will do is that I will just make this into these values of 4 units of 4, and you see that for this 256 I will need 16 such. Okay, so here we have 1 2 3 4 5 6 7 8 9 10 11. So I have to add the remaining one. So I am just making it ready for you. Okay, so I have got it. Let us see how many we have got now. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So now you see that what we need here is, that means that my hash should have these 12 plus 3 15 number of leading zeros. Okay, so that is what that difficulty in bits corresponds to this type of number, and what we need is that our hash should have at least 15 number of leading zeros. Okay, and now we go back and see here whether we had that number. Okay, so this number, so I'm just taking this from here and I am pasting it right below the required difficulty, and if we put it here, okay, sorry, yeah, now you see the rest of it we don't need. So what you are seeing here is that we needed 15 number of leading zeros and then F, and we got this 15 number of leading zeros and 9. So you see that the hash we got, that is less than the desired level of difficulty. Okay. So that is what is meant by this difficulty level, which was actually, if you see, I picked it up from the block header information in terms of bits. Okay. And I converted that using the method that was suggested here. Okay, that how to get to the desired value here, and then convert it into hex, and then we get the required level of difficulty as I simply computed here on the fly. Okay, so is there any question up to this? Okay, so if there is no question, let me point out one more thing related to this. Okay, so you see that with respect to the largest possible target, which meant the easiest computation, which was there in first block. Okay, so if we divide it now the issue is that here we saw that the difficulty bits is written like this, and I deliberately mentioned that I'm picking up from btc.com. Now let me show you something different. Okay, suppose I go to the other explorer, which is this blockchain.com explorer. Okay, and now I go to this same block, so it is 697634. So we'll see it here also, 697634. Okay, now here it is written this block the header information is written a little differently. So if you see that nonce is actually written as a decimal number, whereas here the nonce was written as a hex number. Okay, and if you see here the version is also written as hex here, which was written in hex here. So the versions you see that are the same. But then the difficulty, if you see, it was written in some kind of fractional number like 176 with some decimal values here, and not in the form of this hex number here. Okay, and the particular verification site that I used, that expected that difficulty also to be mentioned in hex. So that's why I picked all those information from the btc.com site. Okay. Now the issue is that this difficulty which is written here in this form, so how was it obtained? So that was actually obtained, as was mentioned here in our slide set. Okay, that this was done as a ratio between these two. Okay, so the difficulty, the largest possible target divided by the current target. So that means that the largest possible target, that is what is given here as 0x this one. So if we get its value, okay, and divide it by the current target, okay, then whatever we get, that will show up here as the difficulty level. So let me also do it for you so that you understand what I am trying to get at, and then point will be pretty clear. So what I will do is that the largest possible target, okay, this is the one that was there in the very first block that was mined. So if I see this, the largest possible target, okay, and now I go to my nice hex to decimal converter, okay, hexadecimal to decimal converter, and I put this value, okay, and I say convert. So I get a very large number. As you see that it's a really large number, and then actually I know that my calculator will not work. So what I will do is that I will use this Google this one here directly in the browser, okay, and the particular value of this difficulty level that I obtained here. So I am picking it up, and then I am again going to my nice this converter. Okay, so I will go to my converter. Okay, and I paste this and I convert it. Oh, sorry, it has got all those zeros, so I just have to get rid of the zeros. So I'll quickly get rid of the zeros for your convenience, so that you understand what exactly is going on. And I'm doing it on the fly for a particular block, so that you also can do the same thing on your own and see that you have full understanding of the thing. So what I have now done is that I have correctly picked up hex value without the spaces, and you see that I have got this decimal number. So I copy it, and then I have this max value and divide it by this. Okay, and I see what it returns, and I see something like this, 17650, and let us see whether it matches. So what I will do is that I will go to my sorry, I will go to this one, and so go to the correct block. Okay, yeah. So now you see that I've gone to explode, and you see the difficulty that is mentioned here is this 16 something. So that is not the hex number, but actual number here, and a decimal number. And now if you see what I could get in my calculation is the same thing, 17650 10 raised to the power 13. So it is 17, 61, 50, etc., etc. And then if you see it also here, okay, so you have the 1765033 here. So you see that in these different explorers, okay, they might represent the same information in different formats. But I just wanted to do the calculation here for you to understand that how this difficulty is represented in this one, and this I could not have directly used for calculating the block hash. Okay, I used it from the btc.com site. Now, there is another reason why I am spending a bit of time in explaining this, and that is that the point is that if I have this difficulty written like this, it is easier for humans to understand. So whether it is going up or going down, okay. So here, if it was written in those hexadecimal digits, then it becomes a little difficult for us to follow. Okay, so that is the reason why I chose this, and we can see that the plot of difficulty level variation. So I will go to the site that shows some of the variations. Okay. So if you see the chart here, okay. So if you see the network difficulty, as I was saying, that here we have this network difficulty in variation like this, and I mentioned yesterday that typically it is going up and up. So if we have some sort of representation of the difficulty in such easily understandable form, you can actually plot it like this, and you can see how things are varying. Okay, of course, these values that are plotted here are not exactly directly what we showed here, okay, as this number. It actually shows it up more as a ratio, but you can get an idea that the way this difficulty is varying also will be similar to way this particular value varies. So it actually tries to do it in terms of another ratio and so on. But that is the reason why some of these explorers show the difficulty in the form of these decimal numbers. Okay. So that is about what is required in order to compute the block hash and how we have the difficulty level varying, and still we can always stick to the requirement, and over time as the difficulty level changes, one has to invest in more computing power. One final thing that I would like to mention here is that let me go back to my yeah, so let me go back here. So we have mentioned that we give this as input and we can calculate the block hash. Okay, now there are a few steps that we have to understand, and that is going on in the background. Okay, so it is not that I just calculate a hash out of these and so on. So these are the steps. So what it does is that it represents all these as hex values. So some of these are already input as hex, like version, previous hash, and so on. Okay, so you see the version is here, previous hash is also in hex, the Merkle root. Okay, the nonce in hex is also here. Now the time, actually this time that we are giving in UTC, that is converted into Unix epochs. So that is the number of seconds from 1/1970, or if you consider milliseconds, it can go up to that. And that number of epochs that you get here, that needs to be converted into hex. Okay, so that is what this time in hex is. So from this timestamp, this is to be converted into hex, first to number of epochs in decimal, and then from there this in hex. And difficulty also, of course, what is there is going in here. Now it is not just that now I have these 6 pieces of elements. It's not that they are just combined and we hash. So what is done is that these are all converted into little endian notation first. So little endian, you know that this will be first, and then this, and so on. So this, for one, you can see that 20A0404, that becomes 0400A020. So that is in little endian, and likewise all of these are actually converted into little endian. Okay, so this is the first step. Then they are concatenated. Okay, so you see that 0400, all these things, they are concatenated. Okay, and then you do this double SHA. But even when you do it, mind it that these are concatenated and they are converted into binary. Okay, then SHA is applied, and then again SHA is applied, and finally that result that we get, okay, that is also shown in this format. So whatever you do through SHA, then again that is converted back. You see this 09 BC, this is reversed, okay, for this little endian notation. Okay, and you get this kind of result. Okay, so this is just to let you know that how actually the hash calculation is done with these as input. So these are the more detailed steps, and if you are a little adventurous, what you could do is that you could actually write these up, and then up to this little endian you might do it yourself, and then after you have done the concatenation like this, so if you wish, you can now convert it into binary, then apply SHA once, and then apply SHA again, and convert that back to hex, and then from there you can convert it back to this, change the endian, and you can get this result. So you can try it out yourself also to get a very good feel of what exactly is going on, okay, while calculating the block hash. Okay, so that is about the block header, okay, and how the hash is computed. Now this is something that we have to keep in mind, and it was mentioned yesterday by Professor Chakraborty also, that currently that roughly about say 100 joules per terahash, okay, that is the energy efficiency. Okay, that means for 1 terahash calculation, you need to spend about 100 joules. And the ASIC hardware for Bitcoin today can perform up to maybe 750 terahash per second. Okay, but then for the entire network, okay, a lot of people are trying, right? It is not that one person is trying. So everybody may have this type of ASIC hardware who are participating, and that for the entire network, it results in like 120 million terahashes per second. Okay, that is from there you can calculate that how much of power is being consumed. So from energy efficiency, if you multiply, okay, you will get an idea about how much of wattage that comes out to be. Okay, so it's a huge waste. And why waste? Because out of so many people trying, only the winner actually will have his block included in the blockchain and will get some fee for that. And the rest actually was attempted, but they failed, and their energy was totally wasted, the energy they spent. Okay, so the entire network consumes, and there are various sources giving different estimates. So roughly about 80 terawatt hours of electricity annually, and as a comparison, an average household in Germany of 4 people consumes about 4,000 kilowatt hours per year. So this whatever this Bitcoin network is spending annually, that could possibly power up about 20,000 households. So this is just a ballpark. Okay, so this is important point to keep in mind, and that's why from here, as was discussed yesterday also, when we feel that it could be only related to a set of known users, may not be trusted, then we may not actually need to go for such highly computationally intensive step of proof of work. Okay, we can have other approaches as we'll study later, and that means that also will save something on the power consumption. Otherwise, within an organization also, the people will be spending a lot of power. And other point that I mentioned yesterday, that you see that very high end hardware is to be used. So you cannot, as I said, that you cannot possibly do it in your own local machines. Okay, so that means that a lot of people will spend their effort, but individually you cannot spend. So what people do is that they pool their resources, or they actually participate. Somebody pulls in money and then they buy the hardware, and that's why they will be able to carry out the mining and maybe win and get some reward. So if you see here for each of these blocks, you see that it is mentioned here different people or groups who have been able to mine those. Okay, so whether it is here or in this Explorer, it is the same, and you can see that many of these are pools. So you see that Binance pool or Poolin or Ant pool and so on and so forth. Okay, Slush pool. So if you see that SBI Crypto, so though it's nothing to do with our State Bank of India, but it is another company called SBI Crypto. So you see that most of these are actually groups who are pulling in their resources, and they are actually able to mine. You will not find Shamik Sural mining one of these. Okay, it is very unlikely. So that is what you need to keep in mind, and they are spending a lot on their hardware and their upgrading. So overall, you may have a question, that is where I end the discussion on the block part, the header part, is that, so what can lead to tampering of the content of the blockchain? Okay, so that means that if I want to tamper a transaction, then I have to change the transaction, change the hash, and change the entire Merkle tree, the Merkle root, that particular block's hash, and the next block's hash, and so on and so forth, till all the blocks currently, and also have to keep going so that no other node can actually mine something which is originating from the correct block. Okay, so it means that as long as so some people have to be honest, okay, so that it will work. But remember that here this tamper proofness, okay, it does not mean that majority of the number of users or nodes are honest. Rather, it is that the majority of the computing power is with the honest nodes. Okay, so that number may not be large, but as long as the total computing power, and if I consider more than 50% of that is with the honest nodes, okay, so then it will work. But if now more than 50% of the computing power is not with the honest nodes, so they can always keep on adding rogue blocks, okay, and that will keep growing because others will not be able to compete with them. So that is what we need to keep in mind. So I thought of mentioning that in this particular context. So now what happens? The blocks say these are mine, and then these are then flooded to everybody in the network. Okay, everybody gets a local copy of the blockchain. So just the recent estimate of the size is only 351 GB. So don't think that it's a huge thing. There are so many. If you saw it here, that the current is closing close to 700,000 number of blocks. But in reality, actually, the size is very small. As you see that it is containing only certain very small amount of data in each block. Okay, so if you join the network, so joining the network is not a problem. Mining will be difficult. Okay, so if you join, you will have to just get a local copy of the current blockchain, which will be about 350 GB of your local disk space. Okay, so she can get the whole copy. Okay, and as a new block is mined, then these all the replicas will be updated. So as you are on the network, your blocks also will be updated, and they have to be consistent. Okay, and they will be similar. So they all will become shared by everybody. Okay, so now we'll move on to the organization of transactions in the block. So transactions are organized as a Merkle tree we have already seen, and if you change, you have to change all these things. So that we all know pretty well. Okay. Now transactions in a block. So if we see that the transactions are organized one transaction at a time, and typically the first one is the one that actually talks about how much of Bitcoin was paid for mining that block. So that is the first transaction, and the remaining transactions in a block, they refer to the actual transfer of Bitcoins to other, from one source to some targets. Okay. I will come to that in a bit more detail very quickly. So just as a representative figure, say transaction 0 that got 100 Bitcoin. So that was its input. Now when it is outputting say 40 Bitcoins to one user and 60 to another. And then in a transaction 1, maybe the user who got 40 Bitcoin as input now sending 30 Bitcoin to another user. So he will have the 10, but there is a little subtlety to it. Now for 60, this one sends 50, so he will have 50 with him, and then as you see, it sends 10, 10, and so on. One point to remember is that if we look at this example here for 40 Bitcoin, actually what happens is that if it got 40, it transfers 30 Bitcoin to another user. Okay, so let us make it say user A, B, and C. So B got 40 from A, and then B is transferring 30 to C. But then it actually has to show that remaining 10 as another output goes to himself. Okay, so that it should have another output 2 of 10 to B itself. Otherwise, what will happen? This will go to the miner. Okay, so first of all, that you have to account for the entire amount. If you do not do that, the rest will go to the miner, whoever is mining that block. That is the first. The other point also is that the miner gets used to for creating the block, and that is what is called, you are now minting some Bitcoin. You are actually, like a mint actually creates new coins. So when you are mining a block, you get some part of the money as your reward for mining that block, and which means that new Bitcoins get added to the network, and that is called minting of the money. And also for each of the transactions, you get a little bit of number of Bitcoin. So that is not new money, that is new coins getting created. Okay. So the miner overall gets two components. Now, of course, that means that the users who are creating the transactions, they should be willing to pay something to the miner to add their transactions to the block. Okay. Now, what it means is that so the user who is carrying out a transaction, say if it is B carrying out a transaction and wishes to pay, say 5 Bitcoins to the miner and 5 he returns to himself. So he will have to say that so 30 and 5 will be there, 5 to himself and 30 to say C, but then rest 5 will go to the miner. Okay. Now, what it also means is that who determines, that question would come, who determines how much to be paid per transaction? Okay. So that could be varying, and the point is that if you do not pay sufficiently large reward for mining your transaction, no miner will include your transaction in a block. Okay. And the miners, what they get it is that they get all transactions all the time. So if you have seen this example, okay, that in Explorer we were seeing, if you remember, that you see these transactions, as you see, they are their transactions, they are getting added to the network all the time in real time. Okay. And these transactions, they go into a buffer for each miner node. Okay. And then they will pick up some of those transactions to create the block. Okay. And if they have a lot of such transactions pending, they may want to actually pick up the transactions they are paying more. Okay. So you have to be careful that if you don't pay sufficient incentive for mining your transaction mining might get delayed. Okay. That is one thing. And but of course you don't want to pay a lot, because then unnecessarily you might be wasting money. So there are different ways of determining how much you can pay and you should pay, and your wallet, your software will actually do that for you. So this is what we need to keep in mind. Okay. And then how things happen. So this transfer and use of the Bitcoins, all these take place through execution of what are called Bitcoin scripts. Okay. So say Alice gives something to Bob. So how will Bob know that it actually came from Alice? So we know that it is through digital signatures. So send the public key of Alice along with signature, and Bob can verify it. Okay, so that is how the information is transferred from Alice to Bob. Okay. Now, actually, these are not these types of signatures that go directly like this. Instead, this transfer takes place using what are called scripts. Okay, so scripts for signature and public key. So there is a script pub key and script sig, which I will explain, which are used for transferring the money. So what happens is that Alice will send, say, 5 bitcoins to Bob. Okay, but then it has to be ensured that indeed it is Bob who this 5 bitcoins was supposed to be, these were meant to be, and then only when Bob can prove that, he will be allowed to spend the money. Okay, so initially when this is done, so for every transaction, Bob must first provide a public key that when hashed will yield the address of Bob embedded in the script. So let me explain that step by step. Okay, so it goes on like this. So say Bob expects Alice to pay him 5 bitcoins. So Bob will send his public address, public key, I'm sorry, the public key, but not only the public key, it should be hashed. Okay, so hash of Bob's public key is sent to Alice. Okay, so Alice makes that 5 bitcoin payment to that hash. Okay, so this is public key payment to this is a payment to hashed public key that is done by Alice. Okay, now that goes to Bob, but then if Bob wants to use those bitcoins, okay, then Bob has to prove indeed that he is the person who is the actual owner of that public. Okay, and that is what is done through these scripts. So what Alice will do is that Alice will embed certain scripts when she sends that 5 bitcoins to Bob, and when Bob wants to spend those bitcoins, Bob has to prove that he was the person who was meant to be to get those 5 bitcoins. Okay, and these are all done automatically through the scripts. Okay, so let us see something. So what is done is that when Alice is outputting the 5 bitcoins, Alice will be using this script pub key along with the payment. Okay, so what is that script pub key? So that has got a number of such steps. Okay, so these are this is an example. Okay, that the script pub key contains. So it says certain operators which are defined in that script. So this is a language which is simple. It has got a limited number of features. Okay, it does not support loops and so on, and it is meant to be secure, so that with loops there might be infinite loops and so on. So it is very simple. It uses these operations. So op dope and op hash 160 and so on. We'll explain what it means. So what happens is that when Alice is sending the money, she also puts the script pub key. Okay, and now when Bob is trying to spend that money, now Bob has to now claim that those 5 bitcoins indeed were issued, were meant to be for Bob. Okay, so when, as long as Bob is not using it, it is lying with him. Okay, those 5 bitcoins with the script pub key as was used by Alice. Now Bob wants to spend that 5 bitcoins, 4 bitcoins to Shamik, and 1 he wants to pay to the miner. Okay, so now Bob is trying to make use of those 5 bitcoins. So now Bob has to use this script sig in order to be able to unlock the 5 bitcoins. So Alice has locked those 5 bitcoins with that script pub key. So what will Bob do? So Bob will have this signature and public key. So what is that signature? Signature is some information like transaction ID and so, which is encoded by Bob's private key corresponding to the public. Okay, and public key is his public key. Now what is done? So you see, it is a stack-based implementation. So the stack is initially empty, and these two are combined. So first you have this script sig as is shown here, and then the script pub key as is shown here. And now it is processed one such step at a time. So sig and pub key are first pushed to the stack. Okay, then op dupe is pushed. What it does, it duplicates the public key. So public key was added by Bob in his this. If you see, this was in his script sig. Okay, so this public key is duplicated. Now this OP hash 160 will do hash of the top of the stack, which was this public key. So this will be public hash. Now OP that public key hash, which was there in the script pub key, that will now be added. And now this OP equal verify, what it will do, it will check that the public key that Bob provided, the hash of that, and the public key hash that was included by Alice, because Alice did not get the public key of Bob. She only got the hash of that public key that was shared by Bob as his address. Okay? So this public key hash was there in the script public key. So OP equal verify will check these two, and if these are okay, that means that it is good. So what it will do is that now it will check for the signature. Now signature is what? If you see, the signature is what was signed by Bob using his private key. Now, using this public key, I should be able to read what was there in the in that digitally signed document from Bob. Okay. So if this public key can decipher that document, that means that was indeed encrypted by the private key of Bob, and hence Bob is the real and authenticated owner of that public key. So it means that not only that what Alice sent to that public key hash that matched with the hash of the public key that Bob possesses, but also that indeed was his public key, because his private key, if something I encrypt with that using his private key like the signature, that can be decrypted with the public key that he is now claiming to be his. So now if these two are matched, then it returns true, and then only Bob will be able to make the payment. So you see that whole thing is automated, and it is covered by the script pub key and script sig. Now we'll conclude with this last slide. So this language that we use, the script, okay, so that is a limited set of operations it has. It has got 256 opcodes, and you can always check in wiki for more details. Okay, but it can handle certain things. Like a simple example I will give, that it can say that that script pub key is not. This is not the only way of showing or writing the script pub key. Okay, this is one example only. Okay, which says that Bob can use it if he can prove that public key actually belong to him. But what can be done is that this money can be locked for a certain period of time. We can say that it cannot be paid before the 1st October 2021. So Alice would put this off check lock time verify here, okay, and before that puts an expiry time. So this whatever in angular brackets, these are constant. So Alice can say this is expiry time is 1/1/2020, 1/10/2021. So now if Bob use it, so this expiry time will be pushed to the stack, and it will be popped, and then it will be checked with the lock time. So it will check this okay check lock time verify. What it will do is that it will check whether the current time is after the expiry time. If not, it will simply close it there, and it will not proceed with further processing, and the payment cannot be done. But if it is after that, then if the rest of the things get verified correctly, the rest of the things you will see are same as what was there in the previous example, then Bob will be able to spend it. So you see that these types of features can all be supported, and there are some other examples that you can make it as it cannot be spent, or anyone can spend, so there is no public key mentioned, and so on. And you can get more details here about the different types of such scripts. Okay. So so that is about the transactions in a block, okay, and how we use this sig pub key and script pub key and script sig to specify and rather lock and unlock the transactions in Bitcoin. So with that, I will stop here. The remaining part we can always take up in our next class to wrap up this set of discussions. Is there any question up to this?
Sir, in the btc.com and all, we see that in each block that is mined, the number of transactions are very different. Some are in hundreds and some are in thousands. So, sir, I mean, when does a node decide that it has to start mining these nodes now?
Yeah. So we'll talk about that in the next one. So some more part is actually there in our discussion. As I said that this is the joining. So I'll come to that in the next class. So as I said that the miners can determine when to actually complete the mining. Okay, what is used to determine that, and we'll also see that there is no particular order in which the different miners will get these transactions. Okay, so they may get in all possible different order, and they will determine when to carry out.
Okay.
We'll take it up in our next class.
And sir, you talked about skipping a transaction if the the user is not willing to pay to a miner. Sir, but aren't we like keeping the transactions sorted according to the time
No,
level?
no, no, it is not, because see that there is no central time to start with. Okay, in a distributed network. Okay, so different miners can, we'll see that, we'll have some diagrams to explain that. So different miners can get these transactions in various different orders. So it is not that everyone has the same sequence of such transactions. The timestamp that we saw was when the block was mined. Okay, that was
Okay.
in the header of the block. Okay, not a timestamp of the transactions. So there is nothing like a physical clock which is synchronized across all the nodes.
Yeah, just to add, means that
Yeah,
particular time is the local time of the miner who has mined the block. Right? But remember
right.
that it's a kind of a complete distributed system, and not only distributed, but distributed asynchronous system. That means the clocks of the individual machines are not perfectly synchronized. And
Okay.
indeed, so protocol you use, so for example, there are protocols like RTP or that kind of protocol for clock synchronization, but that you can synchronize in the order of seconds. But beyond that, you will never be able to completely synchronize the clock of multiple machines in a pure distributed system. Means that is a kind of open problem. So that is the reason that first of all, we do not use the time itself for deciding the ordering of the transactions or for any algorithmic purpose. And the time information which is there in the block header, it is typically a kind of timestamp that is being put by the miner. So it is completely the local time of the miner. Well,
Okay, sir.
Sir, I have one question. So, whenever there is a transaction, suppose Alice wants to send some bitcoins to Bob, this does Alice and Bob need to transmit this transaction information to all the miners in the network separately?
Yeah, so I'll show it in the next class, as I was saying. So each of these transactions will be actually flooded in the entire network. Like it will be sent to one's peers and they will send it to others. And if you get it from two sources, then it will figure out that it is a duplicate, and everybody. So first of all, even if you are not a miner, so if you are a simple node, you will also get those in your system. And after you have got the transactions also included in the block, and and if you are mining, then you will combine a set of transactions to generate a block. Okay, so what happens is that suppose you have got 100 transactions which are not yet included in a block. Now what happens, say you get a block which has say 10 of those transactions. Those 10 will be removed from your, say, we can call it as a cache. Okay, and you will have the remaining 90, and then you get another block then which includes another 20. So they will be removed from your cache, and on the other side the new transactions will keep getting added. So when you are getting the transactions are getting generated, everybody gets it, and anyone can actually validate the transactions. But the mining you can do only if you have the resources, and as the new blocks are created, they will be added to your local copy of the blockchain, and from your so-called quote unquote cache, the transactions that are included in that block will get removed also. Okay, so you know how many of them have actually been included in a block, and also the after one block, how many blocks have been added. That tells us like number of confirmations of that block, which you will see in these explorers also, that it shows that how many have already. So if you just click on one of them, you see that this is confirmation one, means this current block only. Okay, So if you just, so this is the latest one. If you see this 638, so you'll have 5. So that means 5 got added. Now, if you just go to the very first block, for example, okay, that had got, so this is the first one that was, sorry, so if you just go to the block number 0, so this was the one that was, I'll talk about it next day by Satoshi. So he spent this this 50 bit, created 50 bitcoins and sent it to Halfine. So you see that that was now been confirmed by 697643, which is exactly the current number of blocks. Okay, so these are all getting confirmed. Okay, 697642 from 0. So that means that all the nodes in the network will get all these blocks and the transactions, but as the transactions are included in the blocks, they will get removed from that buffer.
Okay, sir.
Any other question?